Okay. So, we will start the last component of the differential vectors, that is curl today. Okay. So, we want to calculate in any curvilinear system. So, if I have to calculate curl, I will use the Stokes theorem. So, in that I know that the loop integral, okay, if I integrate over a loop, then I can write that if I have any vector, say v, which is function of u, v and w, then I can say that v dot dl is actually equal to integral of del cross v dA. Okay, this is the theorem from Stokes. Okay. So, we will utilize this theorem to calculate curl in any curvilinear system. So, here I have, as I have been telling you before also, that u, v, w are some arbitrary coordinates, and u cap, v cap and w cap are the unit vectors, and they are essentially pointing in the direction of increase of u. Okay, u cap, v cap, w cap are in the direction of increase of u, v and w. Okay, if it is decreasing, it will be minus u, minus v, minus w. So, in order to calculate the loop will be on a surface. I can have a loop on a surface. So, let me consider an initial point, say u, v and w, and I give it a small displacement along the u, say, direction, and this is, say, u plus du, v and w. Okay. Similarly, I give a small displacement in the v direction as u, v plus dv and w, and I complete this and I get something like this. Okay. So, here I have u plus du, v plus dv and w. So, this here I have a loop, I go like this. Okay. So, I move on this loop counterclockwise. Okay. And I say that this distance is f du. Now, the reason is quite clear to you all, that why we introduce these notations f, g and h, and here I have g dv. Okay. Is it okay? So, now I can write that dl, small length element dl along the bottom arm is, say, I write dl is equal to f du u cap. Okay. This loop is very small. So, this length, this arm of this loop will also be very small, and I call that small length as dl, a length element dl, that is equal to f du u cap. Okay. So, now what I want to calculate? I want to calculate v dot dl. If I have a vector quantity v, and if it is moving on this loop, then how it would vary? Essentially, I want to find out that. Okay, how that vector quantity would change itself when we move on this loop counterclockwise. So, if I calculate v dot dl, then I get something like this, f vu du. Okay. So, this was on the on the bottom arm, and I have what has changed here, only u has changed from u to du. Okay, and that has been taken into account by writing f du, the change has been considered here. Okay. But here what was my v coordinate? It was v. Okay. So, I have calculated this v dot dl at v. Okay. So, this was due to the bottom arm. Similarly, I can calculate the contribution from the top arm. Okay. And that now you see I have to calculate v dot dl. So, if I have a line element, say a to b, and I have a vector which is moving, which is changing from, or which is moving from point A to point B, Okay. Then if I have to calculate V dot dl, then I write that this should be some function of Vb minus Va, something like this. Okay. So what I am doing, I am calculating at the end points, but here I have a loop. So I will have to calculate the contribution or the contribution in change from each arm, and I will sum them up. Then only I will get V dot dl over a closed loop. Is it clear? I have a vector quantity V which is moving on this loop, okay, and I have to calculate the net change in that vector quantity V when it is moving on this loop. So what I will do? I will calculate the change over each arm and I will sum them up. That will be the total change in that vector quantity when it moves on this closed loop. It starts from here and comes back here. So actually it has to move through these 4 arms. Okay. So I am basically trying to do that. So if I calculate the same thing, contribution or from the top arm, now you see that this is the length is the same, length is same. You are moving in this direction, you are moving in this direction, but the length is increasing in this direction. Okay. So I can write that contribution from the top arm would be equal to minus f Vu du at V plus dV. यही चेंज है और तो कोई चेंज नहीं है. Now I am calculating at V plus dV, only that is the change, no other change. Okay. So the total change, so total contribution from horizontal arms would be equal to f Vu du at V plus dV plus f Vu du at V, and this is equal to minus del over del V f Vu du dV. Now similarly, I can write from the for the vertical arms, for vertical arms I have 2 vertical arms. I can write that the total contribution would be del by del u G V V du dV. From the same analogy, okay, I can write for the vertical arm this would be this. Okay. So I can write that total for just for this loop, only for this loop. Okay. I can write that V dot dl is equal to del over del u G Vu minus del over del V f, ये V है, f Vu and du dV. Is it okay? This is due to the entire loop, the loop which you are seeing here. Now we come here, if what is the area of this loop on which we are moving? dA. dA is equal to f G du dV into W cap. I assume that the vector pointing out of the board. Okay. So that is W cap. So I can write that du dV is 1 upon Fg dA. From here I can write that du into dV here is equal to 1 upon Fg into dA. Okay. So I replace that here. I am doing this straight away here. So I can write here 1 upon Fg dA into W cap. So, what I get here? I get the component along the W cap direction, okay, along the W direction. I will have to calculate similar components along U and V directions too. Okay. So, I do not have to go into the detail of the calculation, just by looking at this expression I can write that V dot dl, complete V dot dl would be equal to, this is along the W cap direction. So, along the U cap direction it would be 1 upon GH and it is W. So, I have UV. So, I will have del by del V and H VW minus del by del W G VV U cap plus 1 by, for the V cap it would be 1 by FH del by del U it will be H VW minus del by del W FVU plus 1 by GH del by del U sorry 1 by FG del by del U GVV minus del by del V FVU. So, this whole thing I have calculated for the entire surface from the same analogy. Okay, I have not done anything. Yes, Shruti, you have a problem. बताइए. Yes, vertical arm it is positive and you tell me why. चाहिए. See, for the vertical arm when I move here I am moving in this direction, okay, and the arm is increasing in this direction, okay. Is it okay? Now I come here and I am moving along the loop. I am along the loop, okay. So, what I calculate? I calculate at Fu plus du minus F du. I calculate the change at u plus du minus u. So, that is positive. In the other case, because the change at v plus dv was negative, so I got a negative change. Because here you see when I am moving here, but my arm is here, okay. So, I was in the negative direction, but you see here I am here at u plus du, I am in the same direction, u plus du, it is positive. I always take, if I have a function, I take f u plus du minus f u, say. This I say is equal to del by del u of f du. I say this, is it okay? So, but if I write it is minus f u plus du plus f u, then it becomes negative. It is equivalent to multiplying it by a negative sign, okay. Now your confusion, I am in this direction, okay. So, it is here positive, everything is fine, but when I come here, actually I am moving in this direction, my length is moving in this direction. So, when I am at u, it is actually equal to minus fu. So, what I am calculating f u plus du minus fu, and it is equal to, this is a positive value. नहीं क्लियर हुआ? यहाँ पे देखिए, ये समझ में आया कि ये पॉजिटिव है, ये पॉजिटिव है, ये सबको क्लियर है? इज इट क्लियर? नाउ व्हेन आई कम हियर एट दिस पॉइंट, आई एम मूविंग इन दिस डायरेक्शन, okay, but my length is increasing in this direction. So, I am calculating change at, I am calculating GVV at u. I am calculating GVV at u, and this is negative. Is it clear or not? This is negative. Is that clear? This is negative. So, it means this is negative. Okay. When I am here at this point, now I am calculating GVV at u plus du. This is positive. Is it clear? Why? The vertical arm is displayed. You see, here at this point V is constant. Okay. So, whatever change in V is there, that I have taken as G, I have taken as G dV. जो लेंथ में चेंज आई वो आपने लेंथ आर्म तो ले ली जी डी वी. अब आपके कोऑर्डिनेट पॉइंट्स ही चेंज हो रहे हैं और कुछ नहीं चेंज हो रहा. व्हेन यू आर हियर यू आर एट यू, यहाँ पे देखिए, व्हेन यू आर हियर you are at u, the whole arm is at u, but when you are here the whole arm is at u plus du. Okay. And the change in V has been taken into account. Change in V has been taken into account. इस पॉइंट और इस पॉइंट में आपने जो लेंथ है वो तो आपने उसको ले लिया, बाकी क्या चेंज हुआ, ये भी तो चेंज हो गया. ठीक है. यदि आप अब आपको यहाँ से यहाँ पे आपको मूव करना है, यू आर टेकिंग द कॉन्ट्रीब्यूशन फ्रॉम हियर टू हियर. सो यहाँ पे क्या चेंज हुआ, इफ यू लुक एट दिस पॉइंट यू सी V plus dV is same, V plus dV is same. What is changing here? U and U plus du at the vertical points, on the topmost point. At the bottommost point U V W. What is changing? U plus du V W. V is constant. Okay. Is it clear? So, we are taking this change, so that comes out to be positive. ठीक है कि नहीं है? So, this is the curl, and I have given you a table, you wrote down a table for U, V, W, F, G, H. So, you just insert the, okay, now we have not completed it yet. So, I can write that, I will complete this. So, from the theorem that V dot dl is equal to del cross V dA, del cross V dA, the whole thing will be inside, there will be an A, dA. Okay. So, I can write that this whole thing on the right hand side is actually equal to del cross V. Okay. From this theorem, if I compare, I can easily say that everything on the right is actually equal to del cross V. So, I can rewrite this expression, I will just remove this dA from here, and what I get here is del cross V in any curvilinear system. Okay, you insert the value of UVW and FGH from that table that I had given you earlier, and you insert the appropriate value. You are in Cartesian, spherical or cylindrical. Is it okay? Now, from here, so this was some basic about the vector algebra or the differential calculus that you would require in doing this course. So, now we move on to actually the electromagnetism, okay, which is your course. So, this was basically we were trying to build up some foundation so that you appreciate this course more. So, now we go on to the law, the physical significance of Biot and Savart law. This you all have heard. So, we will try to understand the physical significance of this law. This is a fundamental law, and this led to the second Maxwell's equation. Okay. The first Maxwell equation came from Gauss law. Okay. We will discuss, we will shortly, I will very briefly explain you that also. Actually the Biot and Savart law gave the second Maxwell's equation, and this was derived from the analogy of the Gauss law. Okay. So what does this law say? So if suppose, do you know, anyone can tell me what is this law about? Okay, what is Gauss law? You don't remember? Yes? Shruti? Anamika? Don't remember. Okay, no issues. We will refresh our memories. So, to understand this, see, always remember that Gauss law is always associated with electric field, and Biot and Savart law is associated with B and S law is associated with magnetic field. Okay. This we all know, this you must be knowing, okay. At least this much you must be knowing. Okay. Then how it is associated? On the basis of these two laws. These are quite intuitive law. I tell you that most of the principles of physics in the first basis of the physics was founded by observation. They did observation again and observation again, and always they found the same result. Then those observations were standardized as laws. Okay. So all these laws are also sort of that type of standardization only, and in the basis is the Newton's law. Okay. So basically the electromagnetism derives its root from classical or Newtonian mechanics. Okay. So if I go back to Newtonian mechanics, if I take two objects, two heavenly objects, and if say I assume that they are circular, but actually they can be of any shape, and if suppose I am able to find the center of mass, if these 2 points represent the center of mass and the distance is r, and if this mass is m1 and this mass is m2, then I say that they will always attract. Okay. But in electricity it does not happen. If I have two charge, depending upon their polarity, they will attract or repel, but there is a similarity. The force of attraction between them, okay, force of attraction between them is proportional to product of the masses and is inversely proportional to the square of the distance between them. Okay. So when I say that I have force field, we are talking about fields now, force is a vector quantity. So at every point here I can assign a discrete numerical value to this force with some direction. Okay. And two different points will have distinctly different direction and magnitude. Okay. I know that as I go away from this point, my force is going to reduce by 1 by r square. So it means it is a vector field, because at each point in this space I can precisely give a magnitude and direction to this particular quantity f. So I call it a vector field. Okay. So this is m1 m2 by r square. So when I have a field, then it means there should be a gravitational field also. There is a gravitational field, and I say that this gravitational field f by m is equal to f by m. So that also goes as 1 by r square. Okay. So let us forget about the field now. So if I come to charge, say I have a positive charge and a negative charge, and they both have charge q and q, and if they both are separated by a distance r, then I say that Coulombian force is also proportional to q1 q2 and is inversely proportional to the square of the distance between them. So this 1 by r square proportionality is common. 1 by r square proportionality is common. Okay. And this, although we can derive now, but at the time when it was these laws were formalized, at that time this was sort of a logical interpretation. Okay. It was logically extracted and then experiments were done and they found that this was always true. So, they were standardized, but later mathematical models were developed. Okay. So, this was about the electrical charges. Okay. Now, what about magnet? Do we have magnetic monopoles? This is a dipole, this is a dipole. So, can I have a magnetic monopole? I know that there are no magnetic monopoles. So, what I will do then? Okay. So, if suppose I have a current carrying loop, current carrying conductor like this. Okay. This is I, this is carrying current. Then it should have a magnetic field around it, and that magnetic field should look like this. Okay. And can you tell me what would be the direction of magnetic field? Anti-clockwise, like this. Is it okay? Okay. So, if I say that this distance is r, okay, if this distance is r, okay, and if this is an infinitely long conductor, then also it has been seen, it has been observed that B is proportional to I. Okay, B is proportional to I and is inversely proportional to R square. Okay. B is proportional to I and inversely proportional to R. Just one second, this is inversely proportional to R. This is magnetic field. This is magnetic field. It is directly proportional to I and inversely proportional to R. Okay. Now, if I have, so this is at this point, if I have a current carrying loop, then at this point the magnetic field would be pointing inside the board. Is it okay? If I have, if this loop goes like this, so here it is a 2-dimensional picture. Okay. If I have to make it, so it is like this. Okay. So, I have something like this, your board is here like this. So, if I take this plane, okay, so here magnetic field is going in and from then it is circulating inside the blackboard and coming out. Okay. So, you have to visualize that here. So, here it is going in and here it is coming out. Okay. Is it okay? So, it means this is perpendicular, in the perpendicular direction, and if I take a small length element dl, okay, along the tangential direction, then this r will always be perpendicular to dl. This r will always be perpendicular to dl. Okay. Now this B, this is what is this? This is magnetic field, B in and B out, penetrating into the board and then circulating inside and coming out of the board, right. So, the direction of B is perpendicular to both R and DL. Is it okay? Direction of B is both perpendicular to R and DL. ये ठीक है? बताइए. Is it clear? Direction of B is perpendicular to both R and DL. It is like this, coming out. So, it is perpendicular to R and DL, and DL and R are perpendicular to each other, because always any radius you draw, that will always be perpendicular to the tangent. Okay. So, it means if I have B, I will have to give it appropriate direction, and I know the direction now. It is perpendicular to both DL and R. So, what I do here, I assume a small unit vector r along this direction, r cap. Okay. So, now I say that B is equal to, I say that small magnetic element dB magnetic field element dB is equal to some constant C, some constant, proportionality constant, I do not know what it is, some proportionality constant C into I, C into I, okay, and I suppose this is R square into dl cross r cap. Is it okay? ठीक है, this dl cross r cap actually gives me the direction to, gives the direction to B, magnetic field. It ensures that magnetic field is always perpendicular to dl and r. ठीक है ये? Okay. So this C is a constant and the value of this C is mu 0 upon 4 pi in SI system. In SI system, this is equal to mu 0 upon 4 pi. Okay. So, if I take the Coulombian system, here also I have a proportionality constant and we call it 1 upon 4 pi epsilon naught. Okay. So, this is a constant, you do not worry about this constant now. When we will discuss about dielectrics, we will try to differentiate between mu and epsilon, but this is a constant and there is a standard way to write it. We always like to write it as 1 upon 4 pi epsilon naught or mu naught upon 4 pi. Okay. To be precise, mu naught is the permeability of free space and epsilon naught is called the permittivity of the free space. So, we all know this. Now, if I have a current carrying, or suppose a wire which is positively charged, it is positively charged, okay. I have a conductor which is positively charged, it will give rise to some electric field. It will give rise to some electric field, and as I move away from this wire, I will see that electric field would reduce. Okay. So, if suppose I want to calculate the electric field at point P due to some element dl, then what I will do? I will calculate here with, you can say, I will put a test charge here, that is the way we do calculate electric field, we put a test charge and through that formula we integrate it. Okay. So, when I have dl here, and when I have dl, I have 1 by r square relationship. But when I want to calculate electric field at point P due to the entire conductor, then what I will do? I will integrate dl. Okay. So, when I integrate dl, what I will get? I will get 1 by r. Is it clear? When I integrate over the entire length, I get 1 by r. Okay. Now, if I have the same thing, if I want to follow here, I cannot do that. I cannot do that just because there are no magnetic monopoles. This is actually an individual charge. This is an individual charge giving rise to some electric field, but this will not hold true in case of magnetic field because magnetic monopole do not exist. Okay. At least till now I have not seen anywhere or in any literature I have not seen where they have quoted that they have observed a magnetic monopole. It does not exist. Okay. And we know that our Maxwell's second equation is actually based on that there is no magnetic monopole would ever exist anywhere. So, if there are no magnetic monopoles, okay, so you just understand here this 1 by r square contribution is because of the individual charge, but because of the entire conductor the contribution would change to 1 by r. So, if I have the same type of, but I know that due to individual charge I say that it is 1 by r square, I have seen that. Okay. So, how can I compare these two situations? So, if I have to compare these two situations, say this is current carrying conductor I and I want to calculate the magnetic field at some point V. Okay. A small magnetic field say dB I want to calculate here due to small length element dl. This is say r, okay, and such that this dl and r are perpendicular. Okay. So, if I want to calculate the magnetic field due to the entire current carrying conductor, what I will do? I will integrate this. I will integrate this and I will get 1 by r relationship. I will get 1 by r relationship. So, I can say just it is a qualitative observation. It is a qualitative observation just by the thing which we have observed here. I can say that these small length element actually act as magnetic monopoles. They are not magnetic monopole, they act as magnetic monopole, because the contribution due to individual charge I take it as 1 by r square, and when I integrate it due to large number of charge I get 1 by r. So, I can say in a way or virtually these small length element act as magnetic charge, and when I have n number of length elements, then they all give me B or integral dB, which is equal to B at P. Okay. So, this is the BO and Savitz's law. So, if I have to get, I will just show you little more about it. I have say a current carrying loop. अभी क्या था, हमारा लॉन्ग कंडक्टर था जिसमें करंट फ्लो कर रही थी. नाउ आई हैव अ करंट कैरिंग लूप. सो फर्स्ट लेट मी टेक positive charge and let me say here negative, and this is positive. Okay, this is an electric dipole, and how the fields would look like, they will start from, or they will sorry, it should go like this, isn't it? It should terminate. Okay, so it goes like this, it goes like this, it goes like this, then I have here, then I have here, and I have something like this. Now, they will be coming out and they will be entering in. So, I have something like this, okay, and something like that. Is it okay? This would be a typical electric dipole would look like this. Now, if I draw an arbitrary surface, if I draw an arbitrary surface here, this is my arbitrary surface with some some area, say dA, okay, then the closed surface integral of electric flux coming out of this surface, closed surface integral of electric flux coming out of this surface is never 0. I know that from Gauss law, but it is equal to the charge enclosed in this volume. Okay, the surface would enclose a volume, it is equal, so it is equal to, I can say that integral closed surface integral E dot dA is never equal to 0, but is equal to charge enclosed in that area. And what is this equal to? Rho, sorry, Q upon epsilon naught. Okay. So, this is the first Maxwell's equation, del dot E. Del dot E is equal to rho upon epsilon naught. Okay. del dot E is equal to rho upon epsilon naught. So, this is the Gauss law, this we call the Gauss law. Okay. Now, we take the now we will try to find out what would be the analogy in magnetic field. When I take magnetic field, I know that there are no magnetic poles, but still I will try to do something. So, when I do this, if suppose I have a current carrying loop, okay, current is going like this, it is again in the surface, okay, we can say that it is something like this, it is like this, okay. So, means here at this point current is going in and at this point current is coming out. ठीक है, ये जो लूप है ये कुछ ऐसा है, ये एक सरफेस है, ये ब्लैक बोर्ड का सरफेस है, तो यहाँ से करंट ये सर्कुलेट करिए, इस पॉइंट पे अंदर जा रही है और इस पॉइंट पे बाहर आ रही है. ओके, इज इट ओके? सो नाउ व्हाट वुड बी द डायरेक्शन ऑफ मैग्नेटिक फील्ड? बताइए. If I have a loop like this and current is moving like this, then what would be the direction of magnetic field? How? Magnetic fields would circulate, isn't it? बताइए. हाँ बताइए. Current is perpendicular to the board, then what is the magnetic field? Apply the right hand screw rule. यदि आपकी करंट ये going in है तो it is going like this, okay. So, magnetic field would be like this, okay, and here it is coming out, so magnetic field would be like this. Is it okay? So, let me draw a clear picture here. ये clear है कि नहीं है? Okay. So, here, so this is rotating and coming like this. So, I have magnetic field here, it is going in, so it will be in this direction, and here I will have in this direction. Okay. And at the center I will have something like this. So, this is okay, and at this point I will have something like this. So, now if I see these two, diagrams, there is a similarity. You do not look in between here, but you look otherwise, you see that the fields are diverging from this point. From this point fields are diverging. Okay? देखिए यहाँ से फील्ड बाहर जा रही है, यदि मैं यहाँ पे कोई पॉइंट ले लूँ, यदि ये वाला पॉइंट जहाँ पे आपका करंट है वो पॉइंट ले लूँ जहाँ पे करंट इज गोइंग इनसाइड, फ्रॉम दिस पॉइंट करंट इज डाइवर्जिंग. Okay. Now, if I try to do the same thing here, I draw an arbitrary surface dA. I draw an arbitrary surface dA, and what are these lines? These are B, magnetic field lines. Okay. Then I cannot say this. I cannot say that the closed surface integral of the magnetic flux over this closed surface is equal to something, some finite value, because I know there is no magnetic charge. There is no magnetic charge. Is it clear to you? I cannot apply the same analogy to magnetic field, but rather I would say that closed surface integral of V dot dA is always equal to 0. it is always equal to 0. Okay. So, this is your second Maxwell's equation, this is your second Maxwell's equation. So, we will continue from here in the next lecture.